I will tell you today a little bit about this company, and also already mentioned this company is a spin-off of the Johannes Gutenberg University. At the moment we are rather small. Two persons are leading that. We have at the moment 3 further persons being involved there, and in Regensburg we are just building up a production site in Schwandorf, and what we're providing is consulting in electrosynthesis. We are a kind of enabler and do also custom synthesis, but also contract R&D. And just to give you an idea, this was founded more than 3 years ago, but we already have break even, and therefore and we grow organically. We were already perceived from the community, for example, by Camp Manager, and in addition you see here that one of the biggest things we at the moment working on is rather inorganic, the recovery of zinc, which will work in a several hundred liter reactor already. Why should we focus on electrosynthesis? And the idea is very, very simple. As you know, for a long time we had coal firing, gas firing, nuclear power plants. We will switch them off for good reasons. And on the other side we have renewable energies, but they come not in a steady way. That means what you need, you can modulate the grid, but this is only in a small fraction viable. You can think about a large buffer system. Usually say if you need the energy of Germany for 1 day, you have to lift the Lake of Konstanz 400 meters higher. This is geologically not possible. Therefore the question is, what can we do else? And the idea is very simple. You generate more wind power and photovoltaic electricity, and then you use that excess energy to make valuable chemistry out of it. Keep in Germany, for example, has 2 terawatt hours per day. We are a heavy industry country still. What can we do? On one side is that we do synthetic fuels. That everybody is talking about that, but most likely, even if you get the electricity for free, it will be very difficult to make a business case out of that. If you make commodities, that means precursors for polymers, it will be a little bit better. And if you go further to fine chemicals, there it's already reality. You can use that and make the compounds. Of course, you need less electricity and the volume is smaller. There are 2 things which is usually totally forgotten. One thing is the selectivity. That means you need to make the compounds in a very selective way. For the fuels, this is almost not important because you can also burn mixtures. But if you go to API, to a pharmaceutical ingredient, then you need it very pure. And on the other side, which is often forgotten in a business case, is the downstream processing. That means if you produce something in water, you have to remove it from water, and this could be quite costly. Therefore, you need a holistic view, otherwise a business case is not viable. That means more or less in chemical sense what you can do. For example, also is for fine chemicals could be fragrances, but also specific building blocks. I will show you some examples. But why should we focus on electrosynthesis? And this is, was mentioned by the American Chemical Society, and where our lab was also mentioned in there. Electricity is really safe because if you switch off the electricity, nothing happens anymore, and therefore no runaway reactions, and you can save a lot of critical elements which come at the moment from Congo or other critical areas of the world. So you bring in the electricity, you take the electricity out. That means you do not generate waste, and this is the most appealing part. Therefore, for the most companies, it's you generate new IP space, a new way, and even shortcut for the synthesis. And this makes it really, really, really interesting. Power to chemicals and green aspects is maybe a more political term, but it's definitely, the Americans call it game changer or disruptive technology. And we believe this is the case. The chemists have this kind of container where they make their reactions. They put the reagents in there, and we just have 2 electrodes which go into this system. The question is, how much does it cost? And usually for molar conversion, it's about, around about 1 euro cent up to 6 euro cent per molar conversion. That's if you buy it as a private person, the electricity. This corresponds to half up to 6 kilowatt hours per kilogram product. It depends a little bit on the molecular weight, but this is affordable. It depends, of course, on the price, on the cost of the electricity. You can do almost everything where electron transfer is involved. That means oxidation reduction is trivial, but you can also start to use the intermediates to make some sequences. That you can work with that, it's very important that you accumulate your product and that you can isolate it later on. This is the key behind that. Just to give you an idea why many people have not used that before, it's not happening everything on the electrode. You start on the electrode, it's the ticket to the party. If you don't control the life afterwards, then you don't make it to the final product. And in between you have many, many parameters. I don't want to go into detail, but you see there's different parameters and some of them are linked to each other. And the question is, what are the numbers we can use, and can we find in a suitable time suitable productive conditions? And some of them is, for example, the current density, which controls how much species you generate on the surface of an electrode. If you do so, what we do is screening, product-driven criteria. That means we look directly, is this possible to make this kind of compound during the process, different electrode materials. This is something we developed 10 years ago, and it's now already sold by a lab supplier. Therefore, many companies who collaborate with us establish their own lab after a while, and we have this we use analytical tools to look into that, but also to be very fast. That means in a couple of weeks we have usually the conditions to work with. We use modern screening tools like design of experiment, even machine learning, and I wouldn't call it artificial intelligence because this is far away from that, to be honest. But you can do also the optimization in that quite well. In the lab it looks like this. Then you do the screening. At a certain point you know what is the best cell that you can go further to larger quantities, like an undivided cell, what you see the upper one, or divided in the middle. And if you go to a significant amount, for example, you want to have 200 or 300 grams, then you go to this kind of stacked cells, and you see in the corner, in the right corner, there's the small screening cell, and the scaling factor here is about 300. That means if you go to larger quantities, you need a flow cell. There's a typical kilo lab. We have on both sides, and in the middle, the flow cell is the smallest part, which operates overnight, and then you collect it and work it up. Therefore, the heart of our technology is the screening technique, that we can have a fast and a good way to find it, and we have to decide afterwards very quickly if we are happy with 1 kilogram or it has to go to unlimited scale up. And then you need the flow cells, which are depicted in the upper arrow. I will show you 2 examples where we did this. One thing is you find in pharmaceutical ingredients often this kind of triangles, cyclopropanes, the red triangles here. It's something which looks like a double bond, but it's not metabolized like a double bond. And one intriguing part, you find them all in different applications against cancer or sleep disorder or antivirus agents. This is one of a very common or very famous one from Gilead, and here's one building block in there. Our collaborator had this several times in his system, and the question was how to make this building block. And the only way to make it on 10 ton was that you start with this naturally occurring amino acid from pig skin, and then you construct, you protect it, construct a 3-membered ring, and then you have to remove the halogens, the bromo functions. And all methods they used had problems that the loss of material was high, or the stereo information was lost. And the idea was, what else can we do? And this is usually when the people arrive at our place, we are the last man standing more or less, because all options were used before usually. And we were pleased to see that this works. By electrochemistry, you see it stepwise, and if you do so, the yield was quite high, but the electrode we used was not that good because we lost a little bit of our material in there. That means we had to use a lead electrode, but you don't want to have the lead in the final product. And therefore, we had to do screening. And the screening was something which was very important to us. Then we found by serendipity a so-called leaded bronze. This is what you see. It looks like a bronze. It behaves like lead, but is very, very stable. And this was used and was also the key. You see, after a couple of electrolyses, you see the lead electrode. This is the gray one, and behind the leaded prongs, which stays really intact. And this was also the reason that we scaled it up. This was the small cell we did for Novartis. We had one which was several times larger and made kilogram quantities overnight. It turned out after a while that the material we got was not that uniform, or is not that uniform as described in literature. But this was the key, because we have several steps. And the reason behind that is, if you look at that, then you see the composition of the electrode, of the alloy, on a micrometer scale deviates a little bit to lead-rich and copper-rich regions, and you need the copper-rich for the second step and the lead-rich for the first step. It's something you do not find by design. Therefore, screening is a really unique and powerful tool. Sometimes this does not work so nicely directly at the electrode, and there's a way we call Excel. That means we make the electrolysis, make a reagent, and then bring it to the conversion. That means in-cell is on the left side, where everything is in one bulb, and on the other one you make the electrolysis and pump it to the reactor container. In this case, you're happy that you can also separate off the hydrogen. The stuff we did was that we made a kind of high performance oxidizers, periodate. This was before, or it's used in labs widely as a good reagent. Unfortunately, if you need high quality, it's not affordable for larger conversions. And therefore, it's usually made on lead dioxide electrodes, and it's contaminated, and you have to purify that. We found a new electrode system for that, bond-up diamond, and now it's very easy to make it. And I will show you that you can even scale it, and you can use the cheapest source of iodine, sodium iodide, to make this. We do use also screening. I don't want to go into details. The conditions are very important that you get it directly. With 82 experiments, we got the conditions to do that. And it's possible that you get 97%, and it outperformed the electrode material, all other ones we could find. Then you go to flow, and then you see already you need something that you have enough caustic soda, and then usually it works. This was a small cell. We went directly to a larger cells, and then you see you can do this easily in 100 to 10 kilograms batches already. And now then you will ask yourself, why are they doing that? I will show you the shortest synthesis of levetiracetam, which is the most common medication against epileptic incidents. And this is the short synthesis starts with aminonitrile, which is made by simple condensation. Then you use the water from the condensation with a genetically engineered enzyme, which was done by our colleagues in Graz. And the last step is the oxidation, which is fueled electrochemically by the periodate. To do that directly gives some side product, and by this way it's a very pure way, and it's the most efficient one which is at the moment on the market. Therefore, we think this is a platform technology we have, and could be very widely used for many other applications. Coming to the last small part, it's about that we have some incineration dust which comes if you burn usually waste from household, there's a lot of zinc chloride in there. This is the reason why this kind of dust has to be deposited in as hazard waste. And the idea was to recover the zinc out of that, because zinc is short, and it wasn't already known from literature how to do that. And our company was able to scale this up. And the important thing is the so-called details in processing, that if the convection is good enough, then you get compact zinc versions, which you can easily later on separate off. On the left side, you see the stuff if dendrites grow, and that falls off the electrode, which is not so good. Therefore, these small keys are very important. And if you know that, then you're able to scale this up in a very nice way. And as I already mentioned, we are working at a pilot plant at the moment with several hundred liters. Therefore, ESyLabs the easy way for our customers. We are an enabler, but of course we also develop our proprietary technology, which brings it further. And at the moment, high throughput screening systems with machine learning are the cutting edge technology, and also new type of cells which make it much easier that this downstream processing becomes highly simplified. And I think this is I'm very happy to be in this company, and of course I'm looking very much forward. And if you have questions, please hit me.
Yeah, many thanks for your presentation. We have one question, perhaps more will come. The first question is, do you have to establish a new process for each different product?
You need conditions for, let's call it like this way, if it's known, and there's a lot of literature out there, even some people don't read it, a lot of literature out there, then you can use that, of course. But if you have a new process, usually you have to adopt it, or you do a kind of screening, but usually in 2 or 3 weeks you have enough knowledge that you can go further. And I think we have examples where you have less than 1 or 2 months to have enough information to think about business case or not.
Yeah. You have mentioned different application areas like fuels, commodities, fine chemicals. I think fuels are not anymore so interesting because they're fading out anyway. Yeah, when we see that after 2030, it will not easy to buy a car using gasoline or diesel anymore. Commodities are still very important. Do you also see a chance for your technology for commodities, or will you focus only on fine chemicals?
No, I think that the fine chemicals is a door opener, definitely. We're already working on commodities, and of course then you have a complete different pressure, cost pressure on it. And therefore I can recommend working together with BASF or Evonik and with a business guy. They will teach you, educate you what to do and not to do. And I think this was a good lesson we learned. And but you have to think a little bit different, unconventional even. And just keep in mind, even vanillin is a commodity. Yeah. Even it's a fragrance, but definitely, yeah, of course, it will come. And there might be even some specific stuff, maybe not fuel, but if you make specific oils, which are later on used as lubricants or something like this. Therefore, I'm absolutely with you. The time of fuel and engines where we burn stuff is terminated. Yeah. Yeah.
Is there a difference between electrosynthesis and electrochemistry?
Yeah, electrochemistry is mostly driven in most cases by physical data. You look at the voltage, current curves. Here we look at the final product. Of course, you need to understand the electrochemistry to make the electrosynthesis. With electrosynthesis, you have to find conditions that it's stable enough for a long time that you can isolate it. You have to merge the knowledge of a synthetic chemist with an electrochemist.
And you're also using specific chemical catalysts in your process?
We use sometimes electrodes, which are catalysts on there, but we try to have, in some cases you cannot avoid it, but we try to avoid critical metals. That means iridium, ruthenium, if possible, platinum group metals, let it out. It should be earth abundant. And if you have carbon electrodes, you do not contaminate the materials with metals. And this is for pharmaceutical industry very important nowadays.
Yeah. And the other question is, to what extent you are planning to scale up the process in the future? And there's my question also, you showed batch processes. Are you limited to batch, or can you also go on non-batch processes?
No, we batch processes usually, in our cases, up to 1 kilogram final product, with 10 liters in total. For the scale up, you need flow electrolysis, and then there's basically no limit. There's one example, everybody knows this fragrance which has the flavor of lily of the valleys, like May, April fresh stuff. This is done by a company in Ludwigshafen with 40,000 ton scale.
Okay.
Electrochemically, and then you see it's scalable, it's possible, but of course there's a lot of engineering. And as soon as the chemistry works, believe in the power of engineers.
That means if you have the right demand, you will also scale up to this demand.
Of course, yeah. And by the scale, the costs will drop as well.
Yeah, sure. Yeah. And if you look to electrosynthesis, how new is it? Since when we can see commercial applications? Is this very new or an older thing?
No. The first example is by Hartmut Kolbe, 170 years ago. Okay. and all the times when crude oil was short, the people used some waste carboxylic acids to make some lubricants and oils out of it. And in nowadays, the people think about it a little bit more. But it was a niche technology for a long time, and now some new ideas come along. It took usually quite long to get a process out of it. And now the new tools, mathematical tools, completely accelerating that.
So a little bit like electric cars. They were also before the gasoline cars.
Yeah.
But then we need technology to really use it. And this is the same here. We need a lot of additional research to really utilize it.
And keep in mind, you have a lot of plants which co-produce electricity, and they have no contract anymore to feed it into the grid.
Yeah.
And for them, it might be an alternative business case now to make something on site.
Yeah, some is to produce hydrogen, some is to use it directly.
Yeah.
And do you have in your process some specific feedstocks, or can you use a wide range of feedstocks?
In the companies or in this company, we look for almost everything. We're not focused on one feedstock. But we, at the moment, in my group, more than half of the group is looking on renewables, which are usually not exploited, like lignin, tall oil, turpentine fraction, nothing which is competing with nutrition. I think that is a big ethical issue. We have to go there. I think it's not to get rich, but it's very important to solve some problems. Because at the moment, it's just incinerated. And before you incinerate that, if you can use it as material, then you deposit CO2 in the cycle where you live, okay? And this helps.
It's sometimes also a question of demand, because lignin is used for vanillin production already on higher scale, but there is not enough vanillin demand to utilize all the lignin.
No. Unfortunately, it's the other way around. The demand is so strongly increasing, especially in China, that still 75% is made from crude oil.
Okay.
And of course, we are working together with Beauregard to make the process even better. And even we try to exploit the craft lignin, which is even much more cheaper.
Well, that's a very important step. I think we have in the world about 60 million tons lignin not utilized, so that's a big feedstock. Yeah.
There are a lot of high-hanging fruits, and reach out for them.
Okay, many thanks, and good luck for the future.
Thanks a lot.